Hello. So last time we started talking about handles, and we decided we were going to restrict attention to dimension 3 and go forward. First, I think I want to say one more general thing about handles, and it's just sort of the general observation or remark. So this is an imprecise statement. It's like a heuristic. The boundary of a handle attachment is a surgery. Okay. To M, say, the boundary changes via a surgery. Okay, so what is the surgery I'm talking about? Well, the idea is if we have some k handle, h sub k, remember this is a copy of dk plus dn minus k. And we're attaching to the boundary of some n manifold Mn. Okay. Well, the first thing to observe is what is the boundary of the handle? Well, it can be split into two pieces. The first piece is we could take the boundary of the first component crossed with the second component. And the second thing we can do is we could do the opposite thing, which is to take the k disk and cross it with the nk minus 1 sphere. And these are glued along this sort of higher dimensional torus. Okay, so maybe we should illustrate this with a picture. Maybe we'll just do this. So suppose we attach a three-dimensional one handle to a surface, or to along a surface. F, which is the boundary of some three-manifold line. Okay, so this is F, and the one handle, H sub 1, is the interval across the two disk, and so the boundary of H1 is S0 cross D2 union I cross S1. So this is two disks, and this is an annulus. And if you remember from our notation, from what I said last time, this is the attaching region. So that means to attach this, we identify a pair of disks in our surface, like this. And what does the actual handle look like? Well, it looks something like this, maybe. These are disks. It's this solid 3-ball, which you can sort of decompose in this way. So this is a 1, and we're going to glue that on. And of course, the result is, so one way you can think about doing this gluing, well, if you think about the gluing, we just stick this on right here. But if we're only concerned with the boundary, what you can think of doing is doing this in two steps. You can remove the attaching region. So this is the S0 cross D2 from the boundary surface F. And then you can attach the other boundary, I cross S1, along the S0 cross S1 boundary. Okay, so So we remove this thing, we puncture our surface in two places, and then we attach on the blue annulus. And so what we've seen, so this would be an example of surgery along a zero sphere surface. And the picture, so maybe as an exercise, you can just think about the picture for surgery along a two-handle attachment should be surgery along one sphere. And so let me just round it out. So in general, what you do is you remove the sk minus 1 plus dn minus k from the boundary of M, and then you attach the other piece, dk plus n minus k minus 1. Okay. So this is what I mean by surgery. So that's the general case. Now we'll restrict. Maybe I'll draw one more picture here, since it's kind of the most important case. So now let's suppose this is F. This is some two piece of our surface F, which is again the boundary of some free manifold Y. And now let's suppose that we have some two-handle H2 that we want to glue on. And what does a two-handle look like? Well, H2 is D2 cross I, and so the boundary of H2 is S1 cross I. So now we see the annulus in the first coordinate union D2 cross S0, and we see the two disks in the second coordinate. So now we draw our three ball a little bit differently. I guess I'm trying to consistently color the attaching region and the is it called the belt region? Okay,
I just call it the free region.
the free region. Okay, I like that. Okay, good. I like having names for things. Free region. Okay, cool. Except that's not the free region. Okay. Blue is the free region. This wasn't in my nomenclature list for handles. Okay, and so we want to attach this along some curve. So what are we doing? We're gluing this thing in here. Maybe we're attaching along this curve, so the core goes to the attaching sphere, goes to that curve. And then the result is, so the two-step way to think about this is to cut this open. So remove, if I go over here, yeah, okay, so we want to remove this green annulus here, the attaching region. I'm going to remove that, and so then I got to get this picture. And then we glue in the free region, the two blue discs. We end up with this. Okay. So the process of attaching this along the surface is surface along this curve. And so let me put down some notation. If F is a surface, and alpha in F is a curve, or a collection. Oh, so maybe I should also take this opportunity to call alpha a simple closed curve. So closed curve meaning copy of S1, simple meaning embedded, and yeah. Or a collection of disjoint simple closed curves. And then from now on, I'll probably just say curve instead of simple closed curve. Let's let F superscript alpha denote the result of surgery F along alpha. So this F and F alpha are naturally connected by this sort of cobordism of handle attachments. But what we really care about here is just how the surface is transformed. Okay, great. Any questions about any of this? Okay. So that was that was one, which we didn't give a name to, so I guess this is part two. All right. So I think we've already talked about handle bodies when we talked about unknotted surface links, but let's just do this for completeness. Genus G, handle body. I could define it to be the thing that an unknotted surface link bounds. I don't think I'll do that. A genus G handle body is a free manifold that is diffeomorphic, a regular neighborhood, or let's say to the closure a regular neighborhood of a one complex in, let's say, S3 with one vertex, G edges. Or I guess you could say with the V vertices, oh, that should be connected. Let's keep it how it is. One vertex. Okay. So of course, you guys know what's going on here. We've got our one complex, and then we thicken it inside 3 space. So we're taking a 3-dimensional regular neighborhood of this thing. This is this nice solid handle. Oh, and this reminds me. So apparently these things were called pretzels. Or bretzel, I guess. Bretzel in like by like Waldhausen and various German people, Germanic speaking people.
Doesn't have a P in German.
No.
This is good to know.
Yeah, bretzel.
I sound like Brexit or something.
No.
Like pretzel.
But I mean, this is, I don't know, this is such a better thing to call a handle body. We should call them either pretzels or bretzels. Because everything's a handle body in low-dimensional topology, so there are handle bodies everywhere. So like I did with membranes with the things, I guess I was tempted to adopt first, but I don't know. Maybe I didn't follow through. I guess this is a genus B pretzel.
What's it actually? What's the joke?
Pretzel. Pretzel is German for pretzel. So,
Ordering pretzel genus 2
or
or 3.
well, to make a pretzel, you take, so to make a pretzel, you take a cylindrical piece of dough, and then you twist it up like this. You make it do some twists over itself like this. The first step. And then you take these little ends and you drag them over onto here. You use maybe like a little bit of egg yolk to make them stick. I don't know. I think this is maybe more twisted than you normally need to put here. And these adjoin when you bake because it rises. This is deceptive because those smush together. So the regular neighborhood you get is something like this. So genus 3, right? So this. Okay. Well, that's something. Shall we take a vote? Pretzel or handle body?
You want pretzel to mean the standardly embedded handle body, or just all handle body?
No, this definition, the genus sheep, I feel a little weird saying pretzel, I think we should call it pretzel. Genus sheep pretzel is a three-manifold diffeomorphic to a neighborhood of one complexity. And then all we need to do is get a better name for a four-dimensional one-handle body, and we'll be in business with some sort of culinary term for that. Pretzel. Okay, all right, and then I guess we'll sometimes denote this guy as Mercury. This is very like pan-scientific lecture. All right, so of course, so one remark is that HG can be built by attaching G three-dimensional one handles to a three ball, a three-dimensional zero. Okay. So the three ball is here. The three balls are the neighborhood of the vertex, and then we attach on these guys. Okay. So this is another thing that doesn't have really a very consistent name in the literature. So maybe we'll call it a cut system of disks, or I think it's also called, maybe I like this better, but a system, maybe of original disks. I don't know, maybe we'll have more votes. For a handle body, is a collection of G properly embedded disjoint disks that satisfy a property such that a regular neighborhood of this collection, what we're left with is, I guess, a three ball. So these things are sometimes called original disks, or they're sometimes called cut disks. The use of the word system is complicated in these sentences for me. Okay, so of course an example of this is that the cocores of the one handles used to build HG, a cut system of disks for the handle body. So we come over here. The cocores, I guess, are going to be these guys up here. Just remember from this picture, this was the, this was a two. This was a two handle. I risked my one handle. Okay. Okay. So then, similarly, we have a definition. An embedded collection of G disjoint alpha G on a closed surface F of genus G. I guess we don't. I know. Is a cut system of curves if the result of surgery alpha along alpha is homeomorphic to. So again, we have that picture. Showing some surfaces here. We have the, maybe now we just have curves. This is alpha 1, alpha 2, alpha 3 on this genus G surface F. And then if we surger, of course, what we're going to get is this picture. Which is this here. Again, maybe these are also called meridional curves. I don't know. I'm not totally satisfied. I've never been totally satisfied with this terminology. But I get the sense that they both are called cut system in a way because, example is if D is a cut system of disks for a handle body H, then alpha equal the boundary of D is a cut system of curves for the surface F equal to the boundary of H. Okay. Any questions so far?
What is the definition of regular number?
Yeah, so maybe here I mean like a small epsilon neighborhood, tubular neighborhood. Oh yeah, it's the word regular, which I don't know. It doesn't mean anything. It just means take a small tubular neighborhood.
Maybe the point is if it's not small enough.
I don't know what the word regular is doing there. Like,
Because we use it all the time.
yeah. The point is, yeah, like Dave was saying, if we take too big of a neighborhood, then it will, you want it to be small enough that it's like deformation attracts back onto the thing, for example. Oh, maybe I should point out that maybe I'll say this. Oh, maybe I won't. This is called the spine of the handle body.
The white thing. Your arrow doesn't.
The one complex.
The arrow doesn't. Your arrow doesn't really point to it. Yeah.
Oh yeah, the one complex. So every handle body deformation retracts onto a one complex, and we call that the spine. That's not super relevant for the time being. Okay, so in the converse to this example, we also have that a cut system of curves alpha on a surface F determines or defines a handle body H sub alpha. Now that I think about it, maybe it should be a superscript. In the following way. So what we want to do is we want to, first step is we attach three-dimensional two handles. Two handles. There's G of them. Three-dimensional two handles to F cross, let's say, -1 to 0 along the curves of alpha cross -1. Okay. Then the second point is that if we then consider the surface F -1, which has been surgered along the curves alpha -1, this is going to be homeomorphic to a two-sphere by the definition of a cut system of curves. And so as a last step, we can cap off this boundary with a three-dimensional three. Maybe I should have gotten off this little down. Okay. We'll draw a picture of this. So we've got our surface F, and then we have some curves on here. Maybe I'll draw simple ones so that we can visualize this. This is alpha 1, alpha 2, alpha 3, alpha 4. So the first thing that we do is we thicken our surface to get F cross I. So you can draw that like this. Let's see how to draw this. This should go. It should go like this. That's not bad. Did I do something wrong?
Or just one. Right, so
Oh, that's fine. Oh, thank you. Yeah, totally. That makes some of those impossible sculptures. Okay. So this guy in here would be F cross -1. We've thickened it down, and then inside, along the images of each of these curves, we attach our two handles. And that cuts this inside surface up into a sphere, and then we fill it in with a three ball. This is H3. And that gives us our handle body H sub alpha. Okay. Okay, I was just going to point out that, maybe over here. Where is it? Remember this third step, this is unique. That's a good thing to remember. Remember, we talked about how every self-diffeomorphism of the two sphere extends to the three ball. This was like because maybe we didn't talk about that explicitly. I guess we must have when we were gluing three balls together to build S3. We said there was a unique way to do that from this Alexander trick. So it's only the two handles. It's only the curves that are contributing information.
And we did that smoothly last semester.
Okay.
Something really mostly presented that result. Smoothly.
Great.
It comes from the Smale, the paper by Smale.
Oh, really?
Yeah.
Okay. Good. Okay, any questions about handle bodies so far? Pretzels? Pretzels? Okay. Okay, so now we have a long definition. Two long definitions. I wonder if I can do them in tandem. Maybe I'll try to do them at the same time. It's like I spend time making these notes and then I just decide to not follow it. It's always a bad idea. Okay. So given a cut system of disks D for a handle body H, and an arc omega living in the boundary of H with endpoints on DI and DJ such that the interior of omega doesn't intersect the boundary of the disks. Oh, yeah, I should say boundary. So it's an arc spanning two of these boundary pairs. Let's consider the three-ball neighborhood, which is given by B, is going to be the neighborhood of DI union omega DJ inside H. So we're going to thicken this in H. So let's get a picture over here. So we have two pieces of H here. Maybe it looks something like this. Here we have DJ and over here we have DI. And this is H with its boundary. And then we have some arc omega boundary. And then what we do is we thicken this whole thing inside so these are meant to be like troughs. This goes into H. It's like a trough neighborhood of omega. And then we thicken this whole thing. So this is the ball B inside H. All right. So let's note that the boundary of B has three parts. We can decompose it as D sub I plus union D sub I prime union D sub J plus. Where this is, this disk boundary, this disk component of the boundary is D sub I plus. This disk component of the boundary is D sub J plus, plus because they're push-offs of the original disks. And then this third piece, which is came from omega and of the other push-offs of the disks. This is D sub I prime.
Do you mean that those are all the, because there's also.
Oh, sorry.
And there's a pair of
Yeah, union P, right, where, good, thank you. It's in here. Boundary of B intersect boundary of H is P, and that's a pair of pants. Thank you. Yeah, there's also the pair of pants on the boundary. Yeah, I'm not interested in that. I will be in the next definition. Okay, and then so we can consider the cut system, or let's just call it collection disks, the collection disks, which we get by taking D, removing D sub I, and adding in D sub I prime. So out with the yellow, in with the purple, and we say that, oh, and then let's call this new collection D prime. So D prime is obtained from D via a handle slide of D sub I over D sub J. That's the definition of a disk. Oh, along conduit. And then similarly, we see that too. Oh, so first we should note that D prime is a cut system. Cut system of disks for H. So that would be because right, so if we cut H open along all the other disks in the system, besides DI and DJ, then essentially what would be left over is we would have surgered the genus G surface down to a genus 2 surface. And we know that cutting open along yellow and orange would give a ball. Well, right, so then since J is also in both of those, it's also cut open along DJ, so now we're down to a torus. Well, there's this ball then that connects, there's a ball in that solid torus connecting DJ to DI. Oh yeah, I guess that's the best way to think about it. Maybe I'll say that. Once you surger along DJ, then DI prime and DI are parallel inside the resulting handle body. Okay. Okay. Two cut systems of disks are slide equivalent if they can be related by a sequence of such handle slides. And this is a little imprecise. What we really mean is that two cut systems of disks are slide equivalent if there's a sequence of cut systems of disks, each of which is obtained from the previous one by a handle slide. And the terminal ends of this sequence are the two cut systems of disks. Okay.
There's no real sense in which it's slide I or J, right? It's symmetric.
Is it symmetric? No. I mean,
In a way.
We removed DI though.
well, there's an implicit orientation of DI over DG. Well, and because we threw away DI.
I wasn't okay.
Yeah. Right. So, for example, if we had slid it the other way, in both cases, you're right. We could have also slid DJ over DI along the same arc, and we would have gotten the same new disk, but we would have thrown out a different multiple. That's a good thing to clarify. Okay. And this really is a handle slide of the two handles corresponding to these disks for each other.
So, Can you slide DI prime over DJ to get back away on 4? Like, is there natural inverse?
Yeah, that's right. So we threw a DI, but yeah, that's right. So then what would that arc be? It would be, I guess, yeah. So maybe that's a good question. So let's just make DI prime a little bit more clear. This disk in here, right, with the trough below it. And yeah, if we slide along this arc, omega prime, if we slide di prime along the arc omega prime over dj, then it will come back towards that. So there's a inverse. Okay. Any other good questions? All right. So the proposition. This is usually attributed to Johansson. I think because it appears in his 1991 textbook, which is that any two cut system of disks for a given handle body are slide equivalent. So this proof is an exercise for you guys in using innermost disks, innermost disk, outermost arc argument. Okay, very similar to when we proved that any two membrane systems for a given trivial tangle are jump equivalent. Same sort of thing. In fact, it's actually maybe a little silly that the order that we're doing these things in now, because this is sort of a more natural first thing to think about, and the membrane systems are sort of a natural second thing to think about. But all right, you guys feel like you could do that? I bet you could. I believe in you. We're going to move along. Many things to do. All right, so now we're going to basically rewrite this entire definition for curves. And now I'm just going to do it. Okay. It wouldn't have been good to do it at the same time because the setup is a little bit different. So we're given a cut system of curves. Yeah, it would have been confusing to do it at the same time. On a surface, yeah. Because not in this definition, there's not going to be any reference to a handle body. Although I guess you could have taken as the handle body defined by these curves. Just like here, we had sort of the boundary curves. In this setup, could be the curves here. But, okay. Alpha I and alpha J, such that the interior of omega intersect alpha is empty. Consider the pair of pants that Dave found, P, which is a neighborhood of alpha I, union omega, union alpha J, sitting on the surface F. So we didn't pay too much attention to these pants before, but it's this annulus connected by a band along omega to this annulus. Okay, let's let the boundary of P be alpha I plus union alpha I prime union alpha j plus. Okay. So here this is going to be alpha j plus, alpha I plus is going to be the boundary of di plus, and the guys would be alpha I prime. Consider the cut system. I'm just going to claim it's a cut system. Alpha prime that we get by taking alpha, throwing away alpha I, and adding alpha I prime. Okay. We say that alpha prime is obtained from alpha via a, I think I'm just going to say a slide. Maybe I'll say handle slide. I think that's more common. A handle slide of alpha I, alpha j, along omega. And two cut systems of curves on a given surface are slide equivalent if they can be related by sequence of constants. Okay, great. And then the corollary here is that two cut systems of curves on a given surface determine or define the same handle body if and only if they are slide equivalent. All right, so that's the story for handle bodies, right? So the upshot is we should really think of handle bodies as corresponding to cut systems of curves on surfaces.
What do you mean by determining the same handle body?
Good question.
Of a fixed genus.
Of fixed genus, yeah. So the natural notion that you probably want is that is homomorphic row boundary, which means the homomorphism should restrict to the identity of the boundary, which is why you want to take care to consider these handle bodies as filling the same fixed surface. So if I took two different surfaces and I took a cut system on each of them, maybe this is a good remark. So maybe I'll just draw some, yeah, okay, I'll draw an example and then turn it over. But to answer your question before I get distracted is diffeomorphic row boundary. Okay, so if I have, say, some surfaces, maybe this one has genus 4, I can determine a handle body by just attaching a bunch of curves. Now the problem is that any, well, oh, I should have let's see. Okay, so these are diffeomorphic. Any two genus G handle bodies. I mean, by definition, a handle body is diffeomorphic to this wedge of circles. So any two genus G handle bodies are diffeomorphic. So by same, we mean diffeomorphic relative rel boundary. So rel a fixed surface. So you really are talking about the same filling of a given surface. Whereas you might have, instead you might have something like this, where you have, so a fixed surface F, and you have some alpha curves. And so the handle body they define, right, we can take any, maybe this is alpha 1 prime, alpha 2 prime, so this is alpha prime. This defines a handle body H alpha prime. They both can be thought of as having the same boundary. But if they're not slide equivalent, then there won't be a diffeomorphism rel boundary of these. You know, in particular, a natural thing to think about is what are the curves on the surface that bound disks in a handle body? Well, every curve that bounds a disk in the alpha handle body can be obtained via slides of the alphas. Same thing for the alpha prime. And if those two collections are different, then the handle bodies are different. And different handle bodies give us 3 manifolds, which we'll talk about next time. Any other questions?
If you have like a different collection of curves that form a right Jesus space of H1, is that?
Yep, that's exactly it. About H1, but H1 of the surface, H1 of F is Z2G, and so what you want to look for is you want the span of alpha 1 through alpha G to span a half-dimensional subspace. They're integers, so they're not spaces. Yeah, good point. Yeah, so that's a good way to computationally check, right? Are we still going?
It doesn't want
It doesn't want to stop?
No, it says more. It's like I click end stream. It says, "Are you sure you want to end the stream?" I say end, and then it brings me back to end stream.
Just have to smash the camera against the wall. Oh, I don't know about it. Oh, the one that was stolen?
Yeah.
Yeah.
I don't know.
So then you can have.
So, remember, fraction of April, I was talking about because I wrote there.
So I saw you talked about this the other day.
That's right.
Yeah.
So, I had tried a 2 co-cycle invariant on the bridge trisection diagrams.
All right, this was like some sort of like threefold 2 cycle.